All right, so next step is let's look at the deformation when we have sort of a uniaxial tension that we apply to this uniform uniaxial tension applied to sort of a structure, a little 2 by 1 millimeter high structure, 2 millimeters by 1 millimeter high, 1 millimeter thick, and roller constraints again clamped here. So this point can't move in X and Y. These points can't move in X, only in Y. That allows for Poisson's contraction. And so when we apply on an edge traction, when we substitute the values for the local element stiffness matrices for, let's say this is a single element, we evaluate the element at this edge. What it reduces to is essentially the same as the 1D quadratic element. And so when we do the integration of this over this area, because it's also in the page 1 millimeter thick, we do this integration, we find out that this load, which is now maybe either Newton per meter or Newton per meter squared, depending on what it's given as, splits 1/6 F, 2/3 F, 1/6 of F of this total force. Okay. Oh, sorry, let me just state this again. So this F is the total force. It can be distributed over this uniformly in per meter or per meter squared, but the total force is F. That total force splits 1/6 F, 2/3 F, 1/6 F. Same as what we saw for the body force in the quadratic front element. Remember, in the body force, we also had that split 1/6, 2/3, 1/6. And so what we learn here is that the body forces in the 1D case and the tractions in this 2D case split the same, because essentially here we have a quadratic, the response of the function. You substitute the values for psi equals to 1 in here, and it's only a function of eta. That function of eta looks exactly the same as a quadratic 1D element. So that is a rationale behind that. Okay. So what we have is we apply here a load of 60 newtons, and now what you need to see is, okay, if you apply a load of 60 newtons, and I divide 60 newtons by 1 millimeter squared. Okay. So what do I expect to see in terms of stresses? Well, the fact of the matter is 60 newtons, 1 millimeter squared, 60 MPa. Okay, so let's see. That's what we expect to see. That's our expectation. Let's see what we see. Undeformed modification factor of 1. That's how it looks. Look at that. Volumetric stress 53 megapascals. Okay, because remember this is now in newtons and millimeters, so the stress is automatically in MPa. 60 MPa, spot on for X, sigma XX. Sigma YY 0 as expected, and sigma XY also 0 as expected. So essentially the only non-zero component is sigma XX. You have to interpret these values and understand that we are working with units, values that have quite large units. So we're working, for instance, in Young's modulus in terms of MPa, and those are the magnitude of numbers. In the context of those sizes of numbers, with the finite precision, this is essentially then evaluated towards a 0. Okay. And so you can see a 53.322 whatever plus this is essentially dust as 0. The 60 plus sort of this dust as 0, and this is nice and uniform across this. If we didn't apply this with the consistent nodal loads, this would not be a nice uniform distribution. This would be some chaos here. So this is why also it's important that we have the consistent nodal loads, so that when we expect to have a uniformly distributed load with a uniform stress across this, as we see here, that we indeed recover that. Okay. So and we can just check also for equilibrium, see that everything makes sense. The reaction force is minus 60, the applied load was 60 in terms of the total force. So that is in equilibrium. Sum of moments is also 0. Okay. So everything works out. Sum of force in Y is also in equilibrium. So this is just one point that's important here, is that for this discrete system, when we work with the discrete systems, that sum of forces, sum of moments, equilibrium must be satisfied for the discrete system, and that's exact satisfaction, okay, with a numerical precision. Okay, so we can see that counts off. So this is important to always do this, make sure that our sanity checks and verification are as expected. Okay, so here's just to show you the results that come back from this, we sort of get this return from this launch function. U reaction forces for me is sigma x, sigma y, so sigma xy, and we can see essentially there's U, and what we know is essentially is all. So if you think about this as the first entry, second entry, third entry, it's not the index number, but just the number of the entry. This is all the odd entries: 1, 3, 5, 7, 9, 11, 13, 15. So all those odd ones are related to the displacement in the x direction, and all the even ones are related to the displacements in the y direction. Okay. Reaction forces, as we know that they are related in the order in which we specified the boundary conditions in our input file. So to see what's going on there, we have to open the input file. So let's open QPatch, pool more, or just like 60 kilonewtons on this pool one. Where's this pool one? So just Q8 patch pool. So I'm going to show you that. Pool more is the other one. So just pool. There's the input file, and there's the output file that gets generated if you run this. So there's essentially this boundary condition, and the reaction forces talk the same language. To understand what the reaction forces mean, you have to open the input file and go and watch these boundary conditions. Okay, so that is important to understand. And then we'll measure sigma xx or sigma yy. And so what is important is that you'll be able to either set up this file from scratch, yeah, or if you're given a file, be able to modify it so that it represents the right loading or the right boundary conditions, or the right material, or Poisson's ratio, or thickness. Those changes you must be able to make based on the problem that I give you. So I'm going to give you a definition of a problem, and you need to be able to drive this input file to solve that specific problem. Obviously, I'm not going to go crazy that you have to measure crazy, generate this insane measure, anything like that. I'll limit it to 1, 2, or 3 elements at most. But what is important is that you can interpret and understand this. So if you want to know what's going on here, you can just visualize. Plot it on a piece of pen and paper. Say where's 0, x minus 0.5y. And you can plot this out and see what you trace out in that case. Okay. So that's essentially what we have. 2D basics. Okay. Then we have the same problem. The only difference is now we're going to apply it. So we're going to pull a bit more. Okay. We're going to, instead of 60 newtons, apply 60 kilonewtons. Okay. And also, just before I continue for this previous one, the displacements that you get out, you can also go and verify. You can verify this with a quick hand calculation of what you would expect to see for a beam. So these displacements that pop back, you're welcome to go and plot them. Sorry, not here, a bit below. Too high. These displacements, if you were to plot those displacements that came back, you are welcome. So let me see if I run this quickly. If I, what's going on there? Everything's running fine, should run fine. So if we do this and we print this displacement U, you can see now here those displacements. You can go and verify whether you agree with these displacements, yeah, in terms of how much it displays, what would you expect to displace in terms of those right hand side nodes, how much must they move. So essentially you have to look at the odd ones. This, all of those are the odd ones, so that's that, and you based on what they represent in terms of the mesh nodes, so this is the degrees of freedom associated with the node numbering. You have to go and be able to really critically identify whether you agree with these kinds of displacements or not. Okay, so that's just to just highlight that it's another thing that we can go and verify. Okay, so where we go now. So that's it'd be good just to do that for sanity check and test for yourself. Okay, so where are we? Okay, so essentially now we're going to pull more. So now we understand what this input file is all about and all that type of jazz. So we can now set up these things up quite nicely. Now we're going to pull with 60 kilonewtons. We can go through the same scenario again. But now essentially this is now the magnification factor still 1. So this is the actual deformation that we see. And let's look at the stress. So what we can see here is that this cross-sectional area is considerably smaller because of the pulling that has happened. Okay, what is important to understand from this showcase here is the stress is always computed relative to the original configuration for linear elasticity. If you want to use this update area for your stress calculation, that's non-linear finite elements. Okay, that means your stiffness matrix is a function of displacement all the same. You have to iterate to solve this thing. This is not what we're doing in this course. This is something you can do. It's called nonlinear geometrical finite elements, and it exists, and it's a well-established theory, but we are not going to do that. We are doing linear elasticity in this course. So what do we expect the stress to be? Well, expect it to be similar to what we saw before. The only difference is it's now 60 kilonewtons as opposed to 60 newtons that we applied. But I would still expect to see something in the 60, yeah, because of this original area. If this was the area that was used, then the stress would be something different, okay? A little bit higher than 60 because this area is smaller. So this is important to understand, okay? So I can go and say, for the hand calc, okay, so the applied load is this what is this, 60 kilonewton. So what would this be? Okay, so this should be 60 gigapascal, or 60,000 MPa, that's what we should see. Ooh, my battery is going now. How much time do I have left? Okay, 10 minutes. So that's essentially what you would expect to see. So let's see what we see out of this. We go here, look at the stresses. That's the strain von Mises stress. We expect to see 60,000 MPa. So just take note, if there's just update the notebook for that, there was a typo there. If you go down, we expect to see 60,000 MPa. Look at that. Spot on, spot on. Sigma YY 0, sigma XY 0. Okay, so that's important to understand. And we can go and check for equilibrium again, make sure that all holds. Go for the displacements, see that we are happy with that, look at the reactions. And when we look at the reactions, we can clearly see 60,000 was applied. And if you go and open this pull more file, we see essentially we applied 1,000, 10,000, 10,000, 40,000. And if you go and watch, say minus 10,000, minus 10,000, minus 40,000, all of those in equilibrium. Again, to understand what these values are, you have to go and look at the order in which we specified the boundary prescribed displacements. For each prescribed displacement degree of freedom, there will be a corresponding reaction. Okay, and the order is given by the order in this input file of the boundary conditions, of boundary prescribed conditions. There's the von Mises stress, there's the sigma xx, sigma yy, sigma xy. You can see nicely 60,000, 60,000, 60,000, zeros and zeros. You can see these values are spot on, spot on. Okay, so that's important to understand. So hopefully this gives you a very good idea of what's going on and where we are. Okay, great. That's fantastic. Thank you.